Okay, so in autoencoder, we have two main things called the encoder and the decoder. So this is what you call the encoder, and this is what you call the decoder part, right? So basically, in a autoencoder, what we are trying to do is to I mean, we are going to reduce the size of the, the weights and biases, not the weight and bias, but the architecture to be exact. We are going to reduce the size of the architecture, and we are going to reach something called the bottleneck, or this is called the latent space, right? So the latent space of the neural network. Now, in that latent space, after the latent space, what we are going to do now, after the latent space, we are going to increase the size of the neural network eventually and arrive at an uh, size where that size is equal to the input size, right? So I told you, for example, we can give it like this. So let's say we are going to like start with the image of 28 by 28, right? Simply a 28 by 28 uh, image. Then we can have 512 dense layer here, then a 256 dense layer, right? And 128 dense layer, and 64 yeah, sorry, now this should be started with we are going to flatten the image, right? So 784, so the input layer will be 784. So then 512, right? 512 and 256, let's say 256, 256, and here we can have 128, right? 128, and finally we can arrive at 64 layer. This is for example, and no need to no need to be the same dimension. This is an example, and like after that, this is a mirror image. Like the decoder is the mirror image of the encoder. That means we are going to have 128, 256, right, and 512, and finally we have this 784, right? 784, and finally we can resize it, and we can obtain like this, something like this, 28 by 28, right? So this is what we can do in this kind of autoencoder. Like this is the neural network architecture of a autoencoder simply, right? Neural network architecture, right? And yes, so then we are going to use this kind of architecture, right, and apply our own data set here. That's what we are planning to do today. Now, the thing is, due to this compression kind of a scenario, uh, something will be lost from the input image, and we are going to get the output. Now, here the autoencoder, the most important thing here is the error function. So if we can declare error function where we can I mean, if we can define an error function, we can do anything using autoencoders, right? For example, what we are trying to do today is to input this kind of image, right? So uh, this kind of image, a noisy image, right? A noisy image of handwritten digits, right? Noisy image of handwritten digits. Understood? And we are going to obtain this kind of an image, right? This kind of an image. And the thing is, now let's say this is X, this is X, and this is X hat, let's say. This image is X hat. And the other thing, we have some other data set as well, right? Our data set like this. So it's like this. Now, let's say that we have a image of image of 2 without noise, right? So let me define this as X original, let's say X original, all right? X original, right? So what we are going to do now, we are going to define an error function. Now I have included only one image here, but we have a data set actually, right? So we have a data set here. So data set is basically now noise images, image with noise, and like image without noise, the same image with noise and the same image without noise. So image with noise is X, image without noise is X O or X original. Now the thing here that you want to like highlight is that we have the both noisy and noise removed image, right? Understood. So what we are going to do now, we are going to define an error function like this, right? In between uh, like XO and X hat, right? XO and X hat. So this is the error function that we are going to build here, right? So what happens here is that we are going to like, okay, after applying this into the neural network, we are going to get an image like this. We are going to get an image like this. So this image, what we can do with this image, uh, we are going to take this image and we are going to get the error between this original image without noise, right? So that means the autoencoder tries to do something like this. When this kind of a image, the image X is given, it's going to take an image. We don't know what's there. We are going to get that image and we are going to get the error between the original image, the X0. So we know that in autoencoder there will be like information loss due to this latent space. Then what happened? The output, the neural network trying to adjust its weights and biases in order to minimize this error. So minimizing this error in the sense like it's going to like make the output image similar to the original image of 2. Or here, for example, here 2. So what's going to happen now? It's going to minimize the error by adjusting the weight and biases. So neural network is going to give an output like the original image. So neural network is here going to, when we are going to input a noisy image, the neural network will remove the noise. So I mean that's what this error function says to do, right? The error function එක තමයි කියන්නේ කරන්න කියලා. Right? The error function tries to do that. Understood? I mean, whatever the output, it's going to get the error between the XO and X hat. So when you are going to get the error, in order to minimize the error, if you are updating the weights and biases, what's going to happen? If you are going to like uh, uh, update the weights and biases in order to train the, I mean, the what you call the make the output image in similar to the original image, the only method of doing it is to output a noise removed image. So that means like here we know that definitely a noise information loss will be there. So the information that's going to be lost here will be definitely noise, right? Since the output image should be similar to the original image. So that means what we have lost, we have to lose is the noise, right? So that's the theory. So that's what we are going to do, right? So let us implement the neural network. So last time we started it and stop it halfway, but today we will hopefully complete the part as well. I mean the whole code, right? So last time, as I remember, we developed the yeah. So sorry about today's arrangement. Like I travel these days in between Kurnagar and Colombo, right? So that's the issue. Anyway, so suddenly I had to travel. That's why. Okay. Anyway, now what I'm planning to do is to develop autoencoder for this application, right? And so let me get an new notebook, right? And Yeah, so last time we already uh, did it, but let me do it from the start, right? Okay, so let me uh, get, get a code called data pre-processing. Data pre-processing. Okay, so yeah, so let me get the maximum space. Okay, right. So yeah, so what I'm going to do, get the MNIST data set. Unfortunately, we don't have a data set like noisy data set, right? So we don't have a noisy data set. So what we're going to do, like we will create that noisy data set by adding some random noise. Then අපේ noisy data set එකක් නෑ මෙතන. එයාට අපි randomly noisy noise add කරලා අපි image data set එකක් හදා ගන්නවා, right? So how we can do that? Uh, you can remember we use the uh, uh, MNIST dataset earlier, right? So can you remember we trained it using a feed-forward neural network? So the same thing will be used here, but now the train data and the train target, we are going to add noise to those images manually, right? And the thing is now we said that in the unsupervised learning, we are not worrying or we are not using labels, right? I hope you can remember. Uh, like no use, or we are not going to use uh, labels, right? So we are not focusing on labels since like what we do, we are dealing with only data, right? So we are only dealing with data. So how we can do that, I mean how we can load it, you can, I hope you can remember these things: load data, and you can load the data. Now the important point here, only data and test data and trained data only will be used here, right? uh, I mean like yes. So I mean targets, test target, train target, no use, right? I mean we are trying to here remove noise from handwritten digits, right? So the thing is now, in order to remove the noise, right, no need to worry about the labels නේද? label එක ගැන worry වෙන්න ඕනේ නැහැ. කියන්නේ දෙකේ ඉලක්කමද තුනේ ඉලක්කමද හතරේ ඉලක්කමද කියලා worry වෙන්න ඕනේ නැහැ. අපි noise remove කරන්න ඕනේ. මොකක් හරි image එක noise එක තමයි අපි remove කරන්න ඕනේ. Understood? So that's what we do. I mean we need to do, right? We are not worrying about the what you call the label, right? So we get the images only. No, the targets or the labels are not required here, right? So the labels and the targets are not required here. And yeah, so that's pretty much everything. And let me yeah, so let me like first divide it by 255 in order to like convert it between a number between 0 and 1, all the pixel values. And I'll do the same thing for the test data as well, right? Test data as well. And thereafter what we can do, like I can get it and let me add yeah, so this pretty much everything. And let me add some noise and create the noisy data set, right? Right. And thereafter what we can do, uh, I can add this random noise. Yes, so train data equals, yes, train data equals train data plus 0.5 into sorry 0.5 into, yeah, 0.5 into np dot random np.random normal. That means I'm going to add the data with a normal distribution. Random normal, and like so then I mean I will explain what I'm doing with this. I mean with noise adding, how this noise adding is done, right? So I will explain it. Before that, let me add the noise yeah, location 0 and scale equals to, sorry, the scale equals to 1, scale equals to 1, then size in size, let me add the size like train data dot shape, right? So similar thing will be done for I mean the test data as well. Yes, so yes, so probably we have to import the numpy first. Okay, now there's an important point, right? So I can add this and I will show you what this does, right? So let me, I mean, no need to do it for this, and I will show you by doing it for a separate thing, right? What means by np dot random dot normal, right? So it's just like, I mean, adding some positive or negative values, right? Positive or negative values, normal distribution. So I mean a normal distribution. So you know what's the normal distribution, right? Uh, like we are going like get some random values in the normal distribution like this, right? And uh, uh, we are going to select the center point as 0, right? So this kind of noise will be added, and this is the size that we are going to pass, right? So that kind of a noise will be added. Now what is going to happen here, I mean, you can see, so train data, and for the test data we are going to add 0.5 into random normal. That means we are going to either add some add a positive value or a negative value to all, I mean to each and every pixel, right? We are going to add the noise to each and every pixel. That's what we are going to do here, right? We are going to add noise to each and every pixel, right? So that can be an addition or that can be a subtraction, right? So we can identify it as a noise basically. So let me plot those two. As PLT, and PLT dot plot. Let me plot the first data, right? Sorry, not plot, PLT dot imshow, right? PLT dot imshow. So this is the test data, I mean the original image. What happened to that? Anyway, I think something Train data, test data. Let me run it again. Ah, here I have replaced it. Train data noisy. I have replaced the original data set. That's what happened. Right. And another thing, let me map into this into gray. Right. So this is the original image. I mean, the test data 0. So let me show you the test data noisy. The test data noisy. Right. So this is the noisy image. Right. So this is the noisy image, and so you can see there's this kind of a thing. But we have to do some other thing here as well, right? So like you can see now the value it's going to add here, right? So that means we are going to, okay, this kind of values are generated, random values, and it will be added to the train data. I mean, that will be added randomly to the pixels, right? So you can see now the value, the pixel value in these images are like we have mapped it into 0 and 1. අපි එක බිංදුව එකටයි map කළා මොකද 255 බෙදුවානේ. එතකොට මොකද වෙන්නේ මේ දාන value එක හින්දා like so the value we are going to add or subtract here. Now there that will be a plus value or a minus value. So it will be added or subtracted, right? Deducted. So what happens here? Sometimes, like let's say, okay, I mean, for example, let's say the value here is 0.9 pixel value. අපි කියමු එක pixel එකේ value එක 0.9. ඒකට අපි හිතමුකෝ මෙතන එකතු වෙනවා කියලා 0.6ක්. මම 0.6ක් එකතු වෙනවා. එතකොට මොකද 1.5ක් වෙනවා pixel value එක. Right? So similarly, like if you are like negative value, let's say 0.2, and if you are going to deduct 0.4, noise එක 0.4 කියලා හිතුවොත් එහෙනම් එතන minus value එකක් එනවා. Likewise, due to the noise addition, right? So the values may like the pixel values may be some pixel values might be there greater than 1, and some pixel values might be there less than 1. So less than 0, right? So what we need to do, we need to clip those things. I mean, we have remove those things, and we have to like limit it between 0 and 1. So that could be done using clip. There's a function called clipping numpy. Test data noisy. I'm going to replace it with np.clip test data between 0 and 1, right? So I'm going to like remove all the values greater than 1 and remove all the values less than 0, and they will be clipped in between 0 and 1. So this will be done for both train and test images. එකන අපි හිතමුකෝ value එක 1.5 තියෙනවා කියලා ඒක එක කරනවා. එකට වඩා වැඩිය ඔක්කොම එක කරනවා. එකට වඩා අඩු ඒවා බිඳුවට වඩා අඩු ඒවා ඔක්කොම බිඳුව කරනවා. Right? So it's called the clock clipping. So after this, let me again plot this and show you, right? So there will be bit different. Yes, you can see now some of the values are clipped, so you are going to see something like this, right? You will see something like this. Understood? So we have a nice little image set with noisy image. Now don't think, okay, what's the purpose of this? We are adding noise. We are going to add noise, and we are going to remove noise using autoencoders, right? For educational purpose, right? So don't think it like that. You can apply it for any other application, but here we are going to add noise, and we are trying to, now these are not a uniform noise, right? So we are adding random noises. So if the autoencoder can remove this noise, that's a big thing. තේරෙනවද? දැන් අපි මේ ඇඩ් කරනවා කවුරුත් මේ මොකක් හරි ඉක්වේෂන් එකක් දිහා නෙවෙයි රැන්ඩම්ලි ඇඩ් කරන නොයිස් එකක් නේ. ඉතින් මේ රැන්ඩම්ලි ඇඩ් කරන නොයිස් එක අයින් කරන්න පුළුවන් නම් අපි ඇඩ් කරපු නොයිස් එක අයින් කරන්න පුළුවන් නම් ඒ කියන්නේ සෑහෙන improve auto encode එක. Right? So that's what we are going to do. I mean, that's something. If autoencoder can remove this noise, so then probably it will, I mean, a good neural network, we can say. Okay, so let me save these things. np dot save train data, test data, and also train data noisy and test data noisy. Right? So then we can run this. And okay, so then probably you can see them here. Test data noisy, train data, and train data noisy. Right? Okay, so we have now noisy and original data set, right? So this is the original image and this is the noisy image, right? So likewise, we have a data set consisting with 60,000 images, right? 60,000 images, the noisy images, original images, and for testing purpose, we have 10,000 images with noisy and also noise removed. Okay, so let me get a new code and train the autoencoder, define the autoencoder and train the autoencoder, right? Uh, so let me train the autoencoder. So from Keras, let me get from layers, let me get input layer, dense layer, convolutional 2D, max pooling 2D, and upsampling. Yeah, sampling. I will explain what you mean by upsampling, right? Uh, Later, but for now, I will include that thing, upsampling 2D, and Keras dot datasets. Sorry, Keras dot models. Let me get the models, import model. I will explain what are these later, right? So there are new things here, and from Keras, import backend as K. Yes, so I will explain about what is backend, what's model, and what's upsampling. But the other things you should be familiar with these through, and like the input layer, I will explain what's the input layer as well, right? And so what we have to do first, define a layer. Now here, as I mentioned last week as well, we are going to, now in this case, we are going to define the neural network, right? And the thing is, in this one, we are going to use, in order to define the neural network, we are going to use a different method here. So can you remember last times in the most of the, I mean, all the neural networks we implemented last time, we created sequential models, right? So you can remember we used sequential models. What do you mean by a sequential model? We are going to first create it like a empty neural network and add layer by layer, right? You can remember sequential models, right? We are going to first define the model and add layer by layer. But today, like if you are going to define this kind of autoencoders and generative adversarial networks, we can't use that sequential method, right? We can't use that sequential method, but we use this method. I will explain what I'm going to do here. So this is a bit different compared to the sequential method, right? So here we have like define layer by layer, not add layer by layer. So in sequential method, we model.add, 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 we added layer by layer. But here we are not going to add layer by layer. We are going to define layer by layer, and we are going to append layer by layer. We are going to append, not add, we are going to append. So let me like define the first layer, the input layer, and then I will explain. Yes, we have a question. Let's see. From Keras.layers. Yes, thank you. Okay, so first let me define the input layer. So input layer will be defined like, okay, so that's the input layer. Now this is how we are going to define an input layer. අපි කලින් input layers define කරලා නේද? දැන් ඔන්න තමයි අද තමයි පළවෙනි පාරම input layer එක define කරන්නේ. මේ method එකේදී input layer එකක් define කරනවා. In this method, not the sequential method, the other method, we have defined the input layer as well. So input layer, we can define the shape of the input layer. So we know the shape here. It's 28 by 1. That means like we are going to add each time we are going to add 20 by 20, 28 by 28 by 1 image, right? And I forgot something. Let me quickly go here and yeah, so we have to add that extra dimension to this data set, right? So let me add the extra dimension before saving. Hope you can remember, right? Train data equal train data dot reshape train data dot shape 0, train data dot 1, right? Train data dot 2, 1. Now you can remember, right? So what we mean here, train data shape is 60,000, 28, 28, 1, right? So let me do the same thing for test data as well. And test data noisy also. I mean train data noisy and test data noisy. Otherwise we can't apply this into neural network. We have to make this 4-dimensional. You can remember, right? You have to remember these things. Yeah, here no need to change now since right, the train data noisy and train data both have the same shape, right? But here we have to change the noisy. Understood now. The shape no need to change since train data and train data noisy has the same shape, right? Yes, hope I did it correctly, and let me save them again. Okay. So then, yeah, so I have created the input layer. So input layer and the input of the neural network is ready to take and input with 28 by 1, right? Okay, here 1 by 1 Nidan images. So you have a neural network which can take 28 by 28 by 1, right? So then what we are going to do, so I have added the first layer. So this is the first layer, to be exact, the input layer, right? So we can say it like input layer, right? So then what we can do, I'm going to add the second layer. So it will be a convolutional layer where we can add layer 1 or encode the layer 1. I'm going to add the layer 1, right? Encode a layer 1. So it will be what I can do, convolutional layer I can add here. Now can you see, I'm not like, we don't have a model here, right? So earlier what we are going to do, like model equal sequential, I mean in early codes. So you can compare it with this, like then model dot add. So this is how we did it in previous examples, right? Previous week's examples. So today not like that. We are going to add layer by layer. Encode a layer 1. So it will be a convolution layer after the input layer, convolution 2D layer. I'm going to define the layer here. So we have like 32 kernels of size 3 by 3, and I can have the activation, ReLU activation, let's say, right? ReLU activation, and the padding the same. So I will explain what this padding same means. Padding same, right? Okay, right? So we have a convolution layer here, the first one. Now then what I'm going to do, right? So this is a convolution layer, right? Now here, I'm going to like multiply it with this input layer. Like it's like multiplying, right? So what's going to happen now? Now we have two, right? So you can see we have two separate layers here, input layer and the first convolution layer. So I'm going to like append the input layer, right? So that means, right? So what's going to happen now? Interesting. The convolution layer will be there, right? The convolution layer will be there, and I'm going to like append it the first input layer 28 by 28 by 1. Right? I'm going to append the layer. So now this will be like, okay, so this both together. Now these are together now, right? So these two are together now. So it has formed a neural network with two layers, right? So then what I'm going to do, now then what I'm going to do, now we have these two here, right? So we have the input layer 28 by 20 by 1, and we have the convolution layer with kernels like this, right? So we have connected those two together, right? Then what we are going to do, right? I'm going to now create another layer, encode layer 2, let's say. And it will be a max pooling layer. Max pooling 2D. Max pooling 2D. 2 by 2. 2 by 2. Max pooling 2D. And padding same. And alright, so this is another layer, pooling layer, and now I'm going to like append this layer here, right? So now what's going to happen, like we have the pooling layer here as well, right? And they are together going to form a neural network, right? Why? Like the encoder layer to the encoder layer, I have appended the input layer. So encoder layer is together with the input layer. Now I'm going to take both and I'm going to append it to the pooling layer, right? Pooling layer, right? Understood? So then what we can do, we can add another layer, right? Let me add another layer of convolutional type. Encoder 1, encoder layer 1, sorry, encoder layer 3. Yes, so the same kind of a thing, and let me append the encoder layer 2 here. Right? So then, right? So then, what we can do, another layer we can add, layer 4. So layer 4 will be the same like, right? Encoder layer 4, and uh, yes. So right. So here, let me add this one, and finally, I'm going to define it like encoder, right? Encoder. So what happens here? Let me show you. Right. Uh, so this is how you have, I mean, define the encoder. Now, thing is now there's a like bit confusing thing. In order to understand this, you need to have the knowledge. You need to have the idea about the convolutional layers, right? Convolutional neural network to be exact. Now, my point here that, like, can you remember when you are going to apply a kernel, what happens, right? Okay, here you can see 3 by 3, 33 kernels of 32 kernels of 3 by 3. So what's going to happen? So you know, like there will be 32 convolutions will be made, right? නේද? kernels 32ක් කියන්නේ මොනවද? kernels 32ක් කියන්නේ kernel 32ක් අපි like we are going to take an input image and we are going to apply 32 kernels of size 3 by 3. So then you know, can you remember? There will be what? There will be right? So there will be 32 convolutions. Can you remember convolutions? And they are like 28 by 28 size, right? And what you are going to do then pooling. When you are going to pool, the thing is now I know that you will be confused here. Now the layer sizes are not reducing, right? I mean layer sizes 32 3 by 3 layer size is not. I mean the kernel size is not reducing. Kernel size එක අඩු වෙන්නේ නැහැ. Again, අපි දන්නවා on encode එක usually like it's like this, no, right? So that means the architecture should be like decreased, right? I mean the size eventually it should be decreased, but here it's not like that, right? What happens here? Actually, it reduces the size, right? Size එක අඩු වෙනවා. ඇයි ඒ? So now we know, right? So we have 28 by 28 image, and when you are going to apply it to a set of kernels of 3 by 3, I mean 32 kernels of 3 by 3, you know, it will create 28 by 28 kernels, right? It's going to create 28 by 28 kernels, 32 28 by 20 kernels to be exact, right? But the thing is, now size is reducing due to the pooling layer. Can you remember pooling layer? It's going to reduce the size, right? So if you are like using 2 by 2 pooling, the 28 by 28 image will be reduced to 40 by 40, right? So then again, we have another convolution layer. You can remember, right? We have another convolution layer. Uh, we have another convolution layer here. Convolution layer size එක වෙනස් වෙන්නේ නැහැ ලොකුවට. හැබැයි වෙනස් වෙනවා මොකද්ද? Right? So it's going to reduce the, I mean, convolution size will be reduced. Then we have another 32 by 30, sorry, 3 by 3, 32 of 3 by 3 kernels. Then we have another convolution layer, sorry, another set of convolutions, and they are like the same size. And we have another pooling layer. We have another pooling layer. So after this pooling layer, the images, set of images will be become 7 by 7. All right. So that's how, due to the pooling layer, the size is decreasing. Right. So at last, what we have, 7 by 7. Right. So it's like this. We input 28 by 28 image, and it's encoded, and finally we are getting 7 by 7, 7 by 7 image, right? 7 by 7 image, right? Understood? Any issues? I mean, if you are, I think this is a bit confusing, so if you have any issues, please ask. I mean, here the neural network architecture is not reducing its size, but due to these pooling layers, the convolution size is, the convolution size of a convolution is reduced, right? Yes, anyone, if you have any issues, please ask. Now, at the end of the encoder, we have 28 by, I mean, we input 28 by 28 image, and we have now 7 by 7 images, set of like 32 7 by 7 images. So if you have any issues, anything unclear, please ask. No, you can't. Now, okay, so we have a question. Can we gradually reduce the convolutions without including max pooling? No, you can't. Since now, let's say, no matter the size, like 28 by 28, the 3 by 3 kernels, right? I mean, here we are using 3 by 3 kernels. So if you go to the basics of convolutions, each extraction, you can notice that whether it will be 5 by 5 or whether it's 7 by 7, no matter what the size of the kernel, right? No matter what the size of the kernel, it will like it will generate images of 28 by 28. The kernel size is not going to be a matter, right? Right? No matter what's the kernel size, it can be 5 by 5, 7 by 7. Anyway, 28 by 28 images will be generated, right? So one and only method to like decrease the convolution size is to include pooling layers, which will reduce the size to like half of, like if you are going to use 20 by 20, sorry, 2 by 2 pooling, then it will reduce the size to half, right? Uh, hope you understood, right? So let us like run this and see encoder dot summary. Yeah, it's taking time. I don't know why. Now, still, we haven't completed the autoencoder. We have only the encoder part. But the first part is completed, right? Uh, yeah, max pooling duty is not defined. Yeah, we can't get a summary. Anyway, we had to get the model. Sorry, we can't get a summary. Now, this is the encoder part, right? So we have created the encoder part. Now we have to create a mirror image of this, right? We have to create a mirror image of this. So that's what we have to do, right? So let me get the decoder layer one, right? So we have to like get the decoder and uh, right. So we have like do it like this. Now what we have to do, like 7 by 7, we have to what do what, huh? 7 by 7, and we have to make it 40 by 40, and when we have to make it 20 by 20, 28 by 28, mirror image. Understood? So that could be done, right? So that could be done like this, right? Uh, yes. So let me add another convolution layer. Let's see. Right. So let me add another convolution layer, right? And decoder layer one. Now encoder and decoder will be basically defined separately, right? They will be defined separately. So then let me add the uh, decoder layer two, right? So decoder layer two. So I will add the, right? Let me add something similar to max pooling, right? Max pooling layer, right? So the opposite of max pooling is upsampling 2D, right? Upsampling 2D. Now, what is going to happen with upsampling? A simple thing, right? So if we perform upsampling, right, like it's like this. You know this. I mean, you know about right. So if you have this kind of a thing, right? So what's going to happen, right? What's going to happen? Uh, okay, so let's say that you have values like this, right? 5, 6, 9, 1. So if we apply pooling, right? Pooling, what's going to happen, right? Like let's say 2 by 2 pooling. Yes, what will be the output? Huh? What will 5691? Yes, what will be the output if you have applied 2 by 2 pooling? Yes, anyone quickly? So if you apply 2 by 2 by 2 pooling, if you can't remember these things, I don't know, right? I mean, Don't think, okay, autoencoder is a different type of a neural network type. No, not like that. We are using convolutional dense and other type of neural networks to build autoencoders as well. So if you can't remember pooling, what's happened in max pooling, right? I don't know. Okay, so if okay, let's say if you have this kind of a thing, okay, so this is like 2 by 2, right? A 2 by 2 2 by 2 matrix. Let's say if I'm going to apply 2 by 2 max pooling here, 2 by 2 max pooling, what's the output that you are going to get? What's the output that you are going to get? Tell me the exact value or set of values quickly. Yes, anyone? Yes, anyone? Okay, let's see. Yes, 9, right? So you are going to get only one value, right? So if you can't remember these things, I don't know, you have to go back. I mean, we are still in the course, right? So if you can't remember these things, that means you haven't like do the, now that's why I'm giving you this weekly assignment or tutorial. So then you have to do something in that week, right? Otherwise, like you can't concrete the knowledge that you are going to gain, right? So this is what you call max pooling, right? So the opposite of this is called upsampling. That means if you can like get this image and I can do something like this. See? I can do something like this. So upsampling. I'm not going to write like sampling. You let me like say upsampling. Let's say 2 by 2. So what's going to happen? So it will create something like this. Let's see. It will create something like this. Right? So from 1, it's going to create 4. Right? So here, what's going to happen? Now here we have like this name, like 7 by 7. Right? So this is what you call upsampling, right? So what's going to happen? Right? So here, what's going to happen? Like in the decoder, uh, we have 7 by 7, right? So 7 by 7. When we are going to upsample it, we are going to get 14 by 14, right? 14 by 14, 14 by 14, right? Understood. So that's what you call upsampling. So then also the decoder, also we had like use that method and append the layers, right? So let me append the layer here. So upsampling, right? So we are getting the like pooling and upsampling, two opposite things, right? And then let me add another layer. Let's say the decode layer 3. Right? Okay, so then let me add another upsampling layer. Now up in this moment we have like 14 by 14 image, right? Like here we are getting 7 by 7, right? Uh, so I mean here we are ended up with 7 by 7 images, set of 7 by 7 images. So then what we are going to do, we are going to apply this and perform the upsampling, and we are getting 4 by 4, 14 by 14, and we have to apply another upsampling, then it will like be 28 by 28, right? So what we are going to do here, another upsampling layer, let's say the decoder layer 4 and decoder layer 3 upsampling, right? So that's it. And finally what we have to get, yes, finally we have what we have to get, right? So here now these are very important points. Now at this upsampling, right? So at this upsampling, we had like, okay, we had 7 by 7 image after the encoder. Encoder again pass 7 by 7 images convolutions. So we apply convolution layer and we are going to end up with again 7 by 7 images. Due to the convolution layer, no dimension reduction is done. Then we are going to do the upsampling and we are going to get like 40 by 40 kernels, sorry, convolutions. Then add another convolution layer. Then we are going to get these kind of convolutions after the convolution layer. Then we are going to upsample it and we are going to get like 28 by 28 images. Then what we have to do now, somehow we have 32 images here. I mean, we have lots of images here, so we have to convert it to a one, right? After image check right? So we have to get only one image, right? We have to get only one image as the output, right? මෙතන 32ක් එන්නේ convolution layer එකෙන් 32ක් kernels we had 32 kernels, so that's why we are getting 28. I mean, that's why we are getting 28 by 28, 32 images of 28 by 28. But according to the theory, we have to get one image input, one image as an output, right? So what we are going to do, finally we are going to add another layer. So the decoder will be we are going to add another convolution layer, and that will be having only one kernel. දැන් kernel 32ක් තිබ්බම තමයි convolutions 32ක් එන්නේ. එක kernel එකක් තිබ්බොත් එක image එක output එක විදිහට එන්නේ. So we are going to get one image as the output, and here let me add the decoder layer 4. Right, so decoder layer 4. Okay. So now we have the encoder and the decoder separately, right? We have the encoder and the decoder separately. So if you have any confusing point, please ask, right? So here we have the encoder, right? We have the decoder. Now you can see it, right? So the mirror image is there, right? So if you compare these two, the mirror image is there, right? Now here, can you see? The input is 28 by 28, output is also 28 by 28. And other, if you compare these layers, it's the same. It's like the mirror image, it's like this. Right? It exactly like this. Right? So what's here? The bottleneck. The size of the bottleneck is 7 by 7. 7 by 7. Right? 7 by 7 image. Right? So 28 by 28 becomes like, so it's there clearly. You can understand. I will show you. Right? So 28 by 28 image input, convolution layer, we are going to get 32 28 by 28 images. Then we are going to pool it 40 by 40. Then we are going to add another convolution layer, and we are going to get 40 by 40, 32 convolutions, and pooling again 7 by 7. So that's the output of the encoder. And that output will be taken, right? And that output will be taken here. And that output again, we are going to like apply convolution layer and do perform upsampling. Then 40 by 40 image will be created. Then again perform upsampling. 28 by 28 image will be taken. Finally, we are going to take one image, one kernel convolution, one kernel 3 by 3. So then we are going to get one output, 28 by 28, one image, right? So that's the architecture of the autoencoder, encoder and decoder separately, right? So we have now here we have the encoder separately and we have the decoder separately. Sequential model now you can identify the difference between the sequential model and this method. So this method, like, we are going to define the layers separately, but at the end we are going to append the previous layer, right, and create the whole model. Likewise, this is how it's done, right? So that's how it's done here. And so we have the encoder here. By after appending all the layers, we are going to append layer by layer, and we have the encoder here, and we have the decoder here, right? So now what we can do, we can create the autoencoder, right? So we can create the autoencoder by what happened? Shit. Okay. Uh, I'm sorry about that. I lost the code. Yeah, first let me get them loaded. And uh, okay, fine. So let me get the code from the GitHub. Okay, I hope this is what we had last time, right? So finally, like, I hope this is what we had last time. And finally, we have the decoder, right? Now combining these two, right? Combining this, the encoder part and the decoder part, right? What we can do, we can create our autoencoder. We can join them and create the autoencoder. So it could be done like autoencoder equals the model. The model is what we included from here, right? Model, and we have to give the two input layer and the output layer. Input layer and the output layer. So output layer is coming from here. This is the output layer, right? So input layer and the decoder. So what you have to give here, the input layer and the output layer. So then we can combine those two layers and create the autoencoder, right? Autoencoder. So that's how we are going to create the autoencoder. Then now this is kind of a normal neural network, a general neural network where we can compile it, right? Compile it, and we can give the optimizers and other stuffs. The decoder part, I think we have to output a sigmoid here, most probably sigmoid. Yes, I hope like that. Anyway, let's see. Okay, so we have a question. Similar to the pooling, the dense layers can reduce the dimensions. Yes, if you flatten the images and then apply dense layers, then yes. Yeah, yes, that could be done. Now, we have a question. Now, if that is the case, so what's the question? Similar to the pooling, the dense layers can reduce the dimensions. Yes. If you flatten the images and then apply to a dense layer and then gradually reduce the number of dense layers, yes, exactly, you can do that. But thing is now, then you are using dense layers, but for image-based application, it's recommended to use. Uh, now you can use it like this as well. Right? So you can flatten the image, right? You can flatten the image and 784, right? 784, then 512. Likewise, you can reduce the number of 10 layers and do the same thing. But the thing is now we are dealing with images, and images, convolutional neural networks are performing well. But still you can do this. So then using the normal things, we can compile the model, the optimizer and the other stuff. The optimizer, the Adam optimizer could be used. Right. The Adam optimizer could be used, and the loss, we can use the categorical cross entropy loss. So the binary cross entropy. Right. Yes. So that's it. We can run and see whether it's working or not. Yeah, it's working. It's giving you the output, but I'm not sure whether any issue is there yet. Dense layers. What do you mean by metrics? Yeah. Sorry. But the thing is now, this is not a classification problem. So this is a regression kind of a problem, right? We are getting the error between pixels. So this is a uh, regression kind of a problem, right? We are getting the error between pixels, each and every pixel. So we can't measure the accuracy, right? So this is not a classification problem. This is the regression problem. So in that case, no need to give the metrics like accuracy. We are not going to see the accuracy. Only the loss would be enough. Right? Can you see what I told you? Right? So input is 28 by 28 by 1. Then we have 32 kernels. Then due to the max pooling, it's going to reduce. Again, a convolution layer, and again reduce to 7 by 7. So this is the bottleneck. Right? So this is what you call the latent space. This is what the latent space is. And these are like, right? So encoded and decoded back. Right? Encoded and decoded back. So you can see the input and the output is the same. Okay, so yes, so then yeah. So shall we train the neural network? Yes, can someone I will, yeah, can someone tell me, okay, the labels and the targets, I mean the inputs and the outputs? Yes. මොනවද දාන්නේ අපි neural network එක train කරන්න බලලා කියන්න බෑ ඉතින්. Good, we have answers, let's see. Both train data, yes. Can you be more specific? We need two things, right? Train data and what we are going to input here to the neural network. Think and give me, I mean, guess. Yes, I mean, like, okay, so when we are training a neural network, I know, right? So when you are going to train a neural network, we need to pass two things, right? So like this, and the autoencoder, not, I mean, not necessary to be autoencoder, but any other neural network also, we are passing two things, right? So we are passing the data. So that's something obvious. Data will be passed, and right. So this is going to give us the predicted data, right? So it's predicted targets, and like what we are going to do, model dot fit data, train data, and train target. That means the data and the actual targets, and it's going to give the predicted targets, and it's going to compare it with this, right? So can you tell me, like, for the autoencoder, what we are going to give as inputs? And I mean, we need to give two things: the data and the target. So instead of data and target, what we are going to give here? Anyone? දැන් model.fit කියන එකට මතකද දාන්නේ? ඔය දාන විදිහට මට කියන්න බෑ දාන දෙක මොකක්ද? Yes, quickly. Original test data before add the noise. Original test data before add the noise. No, no. So my question, okay, let's see others. Noisy data, train data. Yes, good. So train data noisy and train data, right? So what we are going to do now, we are going to add a noise image, and this will give us output. I mean, this is going to give us an output, right? When the noisy image is given, this is going to give us an output, right? So this is going to give us an output. So that output will be compared with what, right? The train data, right? And get the error. So this is the input, and this one will be compared with this and get the error. So that's how, I mean, අනිත් program වලත් එහෙමනේ වෙන්නේ, right? So you have to, I mean, that's something obvious, right? Epochs 100, let's say. Let's validate this as well. Validation split 0.1. Let us train this and see whether it's working. Okay, good. Like we have to spend like 10 minutes for one epoch, right? 10 minutes for one epoch, right? So we can meet on next week and see, right? What's the result? Uh, yes, so I have the same data set and the same thing in Colab. So let us run it there. Otherwise, this will like take 100, like 10 hours, not 10, a lot of time, right? Let us use the Colab. That takes like 10 seconds, right? 10 into 10, 12 seconds. So this will take like 2 minutes, right? This will take like 2 minutes to finish this off. Okay, so now any if you have any like thing to be clarified on this autoencoders, right? Meanwhile, you can ask if there's anything that I need to like explain again, or like anything I need to like clarify, right? Please ask. Meantime, the neural network is trained. Yes, anyone? Now, this, I think, hope you can remember now. We told that we need to apply noise image and get the original image. So you know, right? We have to apply UAT as the input, and the output will be the trained data. I mean, trained data in the sense images without noise, right? The images without noise. So that will be the output. And anyway, the neural network output, the predicted output will be compared with the trained data and get the error. And then the error will be uh, like it will be due to according to the error, the weights and biases will be adjusted, right? So let us like train this, and later then we can apply the test data, right? So we have a set of test data, and we can apply those test data and see whether the noise is removed or not, right? So whether the noise is removed or not. So that's what we are going to do. But we need to first train the neural network and get the weight file, so we can do it in the Colab, and we will train it here, and then we can get the weight file, and we can do the testing in our computer, right? So we had used the Colab earlier as well, right? We use this in our thing is this will take like 20 minutes, right? This will take 20 minutes, not 2 minutes. Like let's say 12 into 100. So that's yeah. So it will take 20 minutes. So we can't wait that amount of time, right? We can't wait like 20 minutes. Let me see whether already trained data is available. Give me a second. I will look for already tested data. So you already trained data. Probably it should be here. Yeah, fortunately we have the H55. So I have previously trained the same thing, right? Previously trained H55. So I can use it in our application, use that in our application. So let me paste it here. Right, so I have the H55. So now the no use of the autoencoder, but you can include it in the autoencoder and train it in the autoencoder. Right? Sorry, you can train the autoencoder in the Google Colab, right? So it will like and like we will implement the code, and we will see the uh, the the loss plot, the validation and the training loss. Then we can get the idea. We can get the idea about the training of the neural network, right? So we will do it later. I mean, after finishing the training. But let us use this file and the h5 file, and let us uh, get some predictions here, right? So let me get a new code called testing the autoencoder. No, 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 like we have a question. Can't we train with 100 epochs? Any specific reason to give? No. No, no any specific reason, but if we stick to the basics, right, we don't know exactly where the knee point is, right? So what I mean by the knee point? Uh, uh, like you know the knee point, right? So we have like plot the loss and see whether we have reached the knee point. So this is where you call the knee point, right? Like this point. So that means this point, after this point, we can make sure that the loss is not decreasing anymore, right? So that means this is the optimal number of epochs that we need to train this. After training this, no use, right? So the loss is not decreasing. That means the model is optimized, right? The training is optimized, so it has achieved the weights and biases. I mean the optimal weights and biases. So this is the optimal. But thing is now at the first time we can't get that idea. Yes, we can create a checkpoint. Exactly, we can create checkpoints. But the thing is now here, if you see, if you check this one, so what you can see, like the the autoencoder, like still you can see now it's decreasing the loss, right? So now we are in the like we are in the 41, right? But still you can see the error loss is decreasing. So we can't stop it at 20, like without knowing like this has reached. Now thing is now if you are going to, right, like let's say, okay, for this example, for this example, uh, so for this example, let's say that you are going to, uh, I mean, you are going to get something like this. Let's say you are going to get something like this, or like this, right? So let's say this is 100, right? So this is not the optimal number of epochs, right? That means like you can see now this is this has a slope like it can reduce like this, right? So that means we have to increase the number of epochs. So that's why I'm using like a big value at the, I mean, a larger number of epochs at the start. So then now after training this, if you can like get this kind of a thing, right? So let's say 100 here. Now after training it, if you are getting this kind of a graph, that means, okay, let's say this is 70. So then we can conclude, okay, it's like it's sufficient to train 70 epochs, since like no need of training 100. But we don't know, we can't like exactly have an idea like this. So we have to train it for number of epochs and we can check the loss, right? So if the loss is optimized, that means, okay, you can change you can stop the training, right? But I mean not stop, you can conclude that, okay, 70 would be enough. But the thing is, if you are seeing something like this at the 100 epochs, that means the error could be further reduced. So what you have to do, you have like increase the number of epochs to 100 and see if you are getting like same graph or if the loss is further reducing, right? So we can't like exactly say this is the number of epochs needed to be trained. First you have to give a first you have to give a number, and according to the number, if you are going to like uh, within that 100 epochs, I mean not 100 but it can be 1000, let's say within the 1000 epochs, if you are going to reach this kind of a knee point, so then you can conclude, okay, this would be enough, the maximum number of epochs this should be trained is 70. But if you are going to train 100 and still there is a slope like the error could be further reduced, then you need to like train it for more epochs, right? So that's how you are going to say. Now there's no any hard and fast rule to identify your I mean identify your give the number of epochs needed to neural network to be trained. We can't exactly do that. What you have to do, just give a random value, not a random value but some big value, and train it and see the graph, and check whether the optimal loss is reached in between those epochs. Otherwise you have to train it for more epochs, right? That's what you have to do. So that's the usual method of doing that. since the loss and everything will be depending on the data set and your application, right? Okay, so then here you can load the, autoencoder. You can load the weights here, load weights, and you can give the file path to the weight file. It would be autoencoders noise removal.h file. So we have loaded the weights now. So then I can get the training data. We haven't used the, sorry, we haven't used the test data, right? We haven't used the test data. Uh, Here you can give it manually, 28 by 28 by 1. Right? Okay, so let me dot predict, right? So let me add the test data noise, right? So so before adding it to the neural network, let me show what I'm trying to do. Import, from matplotlib, import pyplot as plt, and yes, so plt, and let me show you plt.imshow and what's there in the train data. So like we have 10,000 images, right? Train data. MNIST was 10,000 Tiana images, right? And train data 0, right? So let us see, right? Sorry, test data 10,000 Tiana, train data 60,000 Tiana. Yeah, there's issue now. Like we have, can you remember, we have before here, before saving it, can you remember before saving the neural network, the weight and biases, we have reshaped it to like 28,000, 28 by 1. Okay, reshape you can remember this, right? So the thing is now, if you are going to reshape it, the like the matplotlib cannot plot it, so we can reshape it back to. This is only for the plotting purposes, right? So we have to convert it back to 28 by 28. Probably then you can see it correctly. So this is what you are going to see in the test data, right? And this is what you are going to see in test data noisy. Right? So what you are going to do now, so this is the original image and this is the noisy added image. So what I'm going to do now, I'm going to add this test data noise to the neural network. Right? I'm going to add the test data noise to the neural network, and it's going to give me a prediction. Right? Predicted digits. Right? Understood, right? So I just applied those noisy images, right? I just apply those noisy images, and so now we have get some results here, right? අපි දැන් ටෙස්ට් කරනකොට මොකද අපි කරේ noisy images ටික add කළා to the autoencoder, right? So we added some noisy images and it gives us some images output, right? So now what I'm going to do, like how many images are there in here? Yes, how many images are there? Yes, how many images are there? Anyone? How many images are there in the test data? Yes. Yes, good. 10,000, right? So we are going to like input 10,000 noisy image to the neural network, and the neural network is going to give us like noise removed image of 10,000, right? So now what I'm going to do, let us plot those things and see how the results are, right? So let me create a folder called uh, data or results, right? So now what I'm going to do, right? I'm going to include a follow for I in range test data dot shape 0, right? Test data dot shape 0. So you know that this loop will run 10,000 times, right? So this loop will run 10,000 times, right? So each time what I'm going to do, um, let me save, I mean, let me save test data noisy, and the predicted things, right? Uh, show test data I, right? Test data I, and plt dot savefig, plt dot savefig, uh, plt dot savefig, original image plus stri original image I dot jpg or png, right? So that's the first image that I'm going to save in the loop, and we are going to save 3 images, right? So then this will be the noisy image, right? So let me save the noisy image as well, and let me like define like predicted data, right? Predicted data, and here the predicted image. So this is the image given by the neural network. By 9, here it should be I. Yes, we have something in the chat. Let's see. Yeah, it should be I. Then plt dot close. Yeah, the same mirror. Like we have to reshape it to 28 by 28. Otherwise, the matplotlib cannot plot it. Yes, now probably there's. Oh, okay, sorry. Uh, we have to give it inside the folder, and the important point, like I have to map it to gray. So it's creating images. So let me like short by date. Let me ascending order. Yeah. Hi. Okay, so let's see. Okay, so what this means, so this is the first noisy image of the data set, right? Of the test data. Now this is what the neural network gives, right? So this is what the neural network gives. Neural network දුන්න image එක පේනවද? ලස්සන noise එක අයින් කරලා තියෙනවා. And this is the, right? So this is the original image. මේක තමයි original image එක. ඇත්තම image එක. يعني මේ image now for this image we add this noise, right? For this image we added this noise, and when this image is given to the neural network, this is the predicted image given by the neural network, right? So you can see it's like clearly remove the noise, right? And this is the original image, and this is the original, I mean, this is the predicted image given by the neural network, right? You can see exactly the same kind, right? But some things can be there different, but right, so it has removed the noise perfectly, right? Sorry, not perfect. Yeah. I have done. That's why I was like now you can see this is the same, right? I mean, okay, so this is the predicted image. Sorry, this is the original image, and this is the noise image, and this is the predicted image. So this and this are the same. So I have done a mistake. That's why I need to save not test data, predicted data here. Now it might be changed. Let's see. Okay, let me do it like this again. Let me stop this and okay. So this is the noisy image, and this is the original image of that, and this is the predicted image by the neural network, right? So you can see there's a difference between these two, right? Right. They're coming in the order. What's the issue? Date. Anyway, right? Anyway, so let me take two images and compare them. Okay, so this is the noisy image, right? And so this is noisy image one, and this is predicted image one, right? And this is the original image. So can you see? We had yeah, yes, yeah. That's a good suggestion. It's better if you put the for I'll variable as the first letter of the. But the thing is now I I organize. I mean, short it according to the date, right? The time. But anyway, it's fine, right? So for now, yeah. So you can see for one example. So this is the. I mean, so this is the original image, and this is where we add the noise, right? මේක තමයි අපි noise එක add කරේ. මේක අපි neural net එකට දාපුවම මෙයා දෙන output එක තමයි මේක. Right? So can you see now? Like the noise is almost removed, right? The noise is almost removed, right? So if you take another thing, this is the original image of 3, and this is the predicted image of 3, and this is the noisy image, right? So you can see a slight different is there in between the original and the predicted. So it has like identify what to remove, right? So it has identified to what to remove, right? Perfectly, it's removing noise now, right? So if you take another one, so this is the original image 4, and this is the predicted image 4, and this is uh, the noise image 4. Let's see, noise image 4. Yeah, this one. Right, see now these are almost the same, right? So the original image and the predicted image, so that means like it has identified how to remove the noise, right? Understood? Hope you understood, right? So the thing is again, and so if you take the autoencoder in the Colab, now probably it has ended the training. So the loss, if we actually, yes, it's a good mode, but now can you see now it can be further reduced, right? Yeah, loss එක තා පොඩ්ඩක් මේ අඩු වෙන්න පුළුවන් මේ විදිහට යන්න මේක. Can you see now it has like a slight like reducing slope is there, right? Slightly reducing slope is there, but the validation split is almost stabilized, right? I mean, almost optimized, right? So that means like 100 would be enough, right? Okay, so hope you understood what we were trying to do, right? So then it gives us good results, and here also you can see it's giving good results, right? It's giving good results, and it's perfectly removing the noise, right? So any issues or any concerns, anything to be clarified or anything I need to explain again, please inform. I mean, please state if you have anything to be clarified under this autoencoders for this application. Now from this you will get another assignment, right, or a tutorial from this. I will post it tomorrow, and you can work that out. And right, so you can see how autoencoders could be used to remove noise, right? Noise removal applications or denoising applications. Yes, anything to be clarified other than this? I mean, anything related to this or anything related to anything and our course? Now, this is some, I mean, this data set is created by us. The noise is added by us. But I will probably give you an example where like a realistic example to learn this, where you can do your own work with your own data set, right? So it will be, I mean, advanced than this application. And the thing is now, this is a new thing. Autoencoders, the unsupervised learning under deep learning is a new topic. So better you can, if you can like have a good understanding about this, so have a look again about, on these videos and the theory part as well, right? And so if you have any issues, please ask. Otherwise, I will conclude the session for today, right? Since this is the practical session I was planning to conduct, and like we completed this today a bit early, since last Tuesday, like we got the introduction, and so I did it quickly today, since we did a half, we came to halfway of this practical on last Tuesday, so that's why I completed this quickly. So anyway, we have yes, how to train a model if you don't have the image without noise. I mean, no, the thing is now, if you are doing this kind of a thing, you need to have uh, no, you have to have the original image set. It's required. I mean, if you have the noisy data set, you have to find some method of like before training the neural network, you may have to remove the noise somehow. Now you may wonder, okay, if you can remove the noise, then no purpose of having autoencoder, right? Now the thing is, now in order to train the autoencoder, we need to have the original images and the noisy images both. Otherwise, we can't train it. I mean, after training, we can get now. I mean, for this example, what we can do, right, so we can find some old books, let's say, right, with digits, and we can add those noisy images, and probably we can remove the noise, right? I mean, for training, definitely you need to have original data set and the noise data set, both. So any other issues or any other concerns or anything to be discussed? Yes. Yeah, let's say we are creating a model to clean the old photography. How we can do that? Yes, somehow you have to get the, I mean, noise removed one. Right? So we had like use some kind of a Photoshop, some kind of software like Photoshop and other stuff. Then you can have probably remove the noise. Right? You had like remove the noise in order to do that. Otherwise, you can't. I mean, to train the neural network, definitely you need to. I mean, definitely you need to have like image data set without noise. Otherwise, you can't do that. So, have you tried this one? I mean, uh, can we know about the Keras tuner? Keras tuner. I haven't like used that before. Jeffrey, if you have any kind of a reference for that, please send me. I will have a look probably. Uh, I'll have a look and let you know. But yeah, so okay. So I'll look into that and let you know. And about this, so what happened to this? I mean, the contact. Right. So this custom, sorry, training object detection for API for custom object detection. So what's the progress of this one? Anyone? Like, did you able to finish this one? Have you tried this out? Anyone faced any issues or anyone needed any help regarding this one? I just give you a tutorial to cover that thing, right? So what happened to this? Did you try it? Any it like the cat and dogs data set? What happened? Yes, you didn't try it. You will try it. Yes. No GPU, but exactly, but without a GPU you can do that, but it will take some time. I mean, few days, but you can keep it in your computer and you can do other works. It's fine. Anyway, I have finished creating the video tutorial for this. Probably I will upload it in this week, so then you can have the video tutorial and do it again, right? But it will take, as I mentioned, it will take some time, a few days to train this, right? You can't do it in the Google Colab, right? Since like it will take several days, and also you can't configure Google Colab for this kind of a thing. It's a bit hard, right? Okay, so any other thing to be discussed? Right, so now another important thing that we had to shift now, like the Saturdays, now today onwards, the Saturdays we have to do the practical session, and on Tuesdays we have to do the theory session, right? Due to the due to what happened on last week, right? So today we did the practical session. So on Tuesdays we have to do the theory session. Otherwise we have to like skip 1 week. Like we have to miss another Tuesday, and we have to do. But I think it's fine to do the theory session on Tuesday, right? It's fine, right? Any concerns? Now today onwards, due to the like what happened on last time, we have to conduct now the practical session on Saturday and the theory session on Tuesday. I hope it's okay with you, right? Yes, anyone having any issues with that? Okay, sometimes we are unable to participate due to the office work on Tuesdays. Is it? Okay. Uh, Better to continue lectures on Saturday. So we have a suggestion, like to continue the lectures on Saturdays. Yes, others. So we have a request. Others, do you have any issues? I mean, we have. Uh, I got a message from one saying that better to conduct lectures on Tuesdays. Like they are, like sometimes they are unable to participate on Tuesdays. Yes, other anyone having that kind of issue? Any suggestion? Okay, let me see, and I will let you know about what to do for that kind of issue, right? So I will see that, right? Okay. Uh, Anyway, so any other thing to be discussed? Otherwise, I will conclude the session for today. And if you have anything, please ask if any issues to be, anything to be discussed. So I will give you a tutorial on Autoencoder, so practical application where you have to do your own work, and it will be probably published on tomorrow, where you have to start working on that. And please submit your assignment, right? So if you are not submitting your assignment, you will not get marks for the. I mean, if you are expecting to get a certificate with the grade, if you don't have the assignment, as I mentioned in the first week, you won't get the grade, right? Okay, so then thank you very much, and meet you on next day, and I will let you know what to do with this class shift. And uh, so do your work and have the, I mean, if you can't remember anything, please watch the video and keep in touch, right? Okay, so thank you very much, and meet you on next time, and good night.